So our next speaker is Rachel Cummings. And Rachel comes to us from Caltech. She's an assistant professor of industrial and systems engineering and computer science. About a year ago, I was putting on a conference for statisticians involving the southern states. And I was looking for people to give a talk on data privacy. So I asked 3 or 4 of my statistician friends that I thought knew about data privacy to give me some names. And one thing is most of them gave me names of computer scientists, not statisticians. And the other thing is every list that I got had Rachel on it. So
Wow.
We're very happy to have her be at this conference. Welcome, Rachel.
Thank you. So perhaps this talk is very appropriate given the recent conversations that we've been having about about the trade-offs between privacy and kind of like a usefulness and the appropriate measure. And in particular, for the last question, if these companies are really incentivized to exploit our data, do we have any other options? And in my talk today, I'll give some tools that might actually help incentivize companies to give better privacy protections to their users. And I do have a minor speech impairment, and so if I pause briefly during the talk, I promise I'm not just daydreaming. So I think it's not surprising to this room that privacy concerns affect behavior. And so there was a, I guess now slightly outdated Pew Research study finding, in fact, that most adults do things online to avoid being surveilled, and this may be changing how they browse, deleting history, things like that. But as we also talk about data science and machine learning, really this behavior is your data. And so this is your browsing behavior, this is your GPS activity, and this is how you behave on an app. And if you delete or change that data, then it means that we're not going to be able to pass on correct information that can then enable accurate machine learning. And so the economics interpretation of this, of the fact that people change their behavior based on privacy, is that, well, that means that a person's utility function must incorporate privacy. People care about privacy. And for those in the room who are not economists, utility function is just some kind of underlying objective of your life, and your goal in life is to maximize utility, and that function incorporates everything that you care about. Maybe it's privacy, money, life, happiness, family. All those things in theory are involved in some very complicated function. And so then really, what's the utility for privacy? How do we value it? Because if it's a thing that is valuable to people, and it's also valuable to companies, or perhaps a lack of it, then we can start talking about market design for privacy. How can I buy, sell, or price data? And what is a fair price for your privacy? And so if we can quantify the value of this object, then we can apply all of our economic tools to it and bring those to bear. And so in theory, economists assume everyone is a rational utility maximizer, and they have some function, and they just do the best thing according to that function. But in practice, that's not quite how people behave. So this was a performance art piece where the artist asked people to give up their name, photograph, fingerprint, mother's maiden name, and the last 4 digits of their social in exchange for a cookie. And by and large, people did it. So I don't know about you, but this does not sound like a rational person to me. So there's some question about trying to model this on the personal level. And so now let's, for a moment, put on our philosopher hat. How do people value privacy? Why is it important? And by and large, privacy philosophers give 2 different versions of why we care about privacy. And the first one is an intrinsic value. And this is a thing that is important to us. It feels right. It's a fundamental right. It's creepy if my privacy is violated. All these things are very real. And this is kind of a touchy-feely internal notion. On the other side, we can also talk about the instrumental value, which is saying, I believe that my data today are going to be used against me in the future in some direct way that affects my happiness, money, life. For example, I might be concerned that if I have my medical information shared, it may affect my insurance prices in the future. And the nice thing about this is that it's really easy to put a dollar value on it. Because I'm like explicitly saying in this version, there is some dollar value associated with my privacy. And so today, we're going to work in this space because for that, it's a whole lot easier to do math on. At my core, I'm ultimately a mathematician. And so today, we're going to be talking about repeated auctions where some learning occurs over time. And so for those of you who think this doesn't really apply to your life, so in fact, this is how nearly every single targeted ad that you see online is placed. And so those ads are sold by auctions, and there's some learning that is happening about you over time. What things do you like? Where do you live? How? And your age. And so those things go into the advertiser's value for you. And so the advertiser is going to bid based upon how appropriate they believe their ad is to you. Today, we're going to completely abstract away all of that. We're just going to talk about auctions. But this is an example story to keep in mind of how these things actually do have a very direct impact on our lives. So if I say auction, think about this picture. So there's some bidders over here, and they have values all drawn from some commonly known prior distribution. And there's an auctioneer over here who knows this F, this common prior, and she's going to design some rules of the auction. And for those of you who have not thought about how auctions work before, we're going to have one very fast crash course on this field that's called mechanism design, which is really a challenge of just how to design auctions. And so I don't expect anyone in the room to be an expert, and so this slide is the only things you'll have to know during the talk. So at its most basic form, auctions take in bids, and they spit out two things. So they spit out an allocation, which is who gets what, and a payment, which is how much you pay. And there's this thing called the payment identity, which says really, so this allocation is actually the only part that's important, because from some allocation, I can just immediately compute payments. And we're going to be talking a lot today about a very famous auction, Meyerson's, and it can be summarized as a second price auction with a reserve. Second price auction means that the highest bidder is going to receive the item, and they pay the second highest bid. And so that's where its name comes from. And this reserve can be thought of as the seller's bid. How much do they value keeping this item for? And so people have to bid above the reserve price to win. And so think of this as the seller is really committing to sell the item less often, because it might be the case everyone bids below the reserve. But if they do sell it, then it's guaranteed to be at a higher price that is at least this reserve, because that counts as a bid that they have to compete against. And I'm going to be talking about the Meyerson reserve, which is really just the optimal reserve for the seller who wants to maximize revenue from the sale. And that will depend on this common prior F and some properties of the auction. I won't tell you how to compute this, but it's known. And so if I say Meyerson reserve, think about that. And it also extends pretty naturally if I have more than one thing for sale. And a very nice feature is that it encourages players to bid truthfully. And so their bid is going to be their true value, and that's great. Questions about this stuff? Cool. Okay. All right, and so back to our picture. And so here's a classical view, how we have this common prior that is known to all players and to the auctioneer. And so then she can just, for example, compute the optimal reserve price. Great. But that's not how the world actually, that's not how the world actually works. Really, this auctioneer doesn't have like a complete information of how the world works, but instead she probably has some like past bid data. And so she might run this every day and have some like historical data about how bids tend to go. And she can use that to form some approximate belief about the prior. Great, and so then she can just like compute optimal things based upon the empirical data that she's seen so far. And we have a lot of work on the computer science side about like how many samples we need to be able to like compute the optimal auction. And I'll say this is a very incomplete list, but this is a few. And so really, if the auction is truthful, and these samples truly are samples from the true underlying value distribution, and then if you have enough observations, then you can just like do lots of optimal stuff and get high revenue. Great. But I have a concern that the underlying auction is actually truthful. And I'm concerned that the samples that we're getting are in fact not true samples, but they are like strategically chosen. And the reason why is because this is how the auctions actually work. And so maybe on day one, we had this auction, and these guys bid. And then on day two, then like the same guys appear again, and the same auctioneer now has knowledge of their past bids. And if this happens over and over and over again, it's really easy to see how this is not truthful, and players, in fact, should not share their true values. And so a challenge is having like nice incentive properties in these multi-round games for the same players participate over and over again. And it would be really nice if we had some technical toolkit to like decouple incentives across rounds. And so maybe I can say, for your bid today, won't affect outcomes, be it allocations or prices in the future. That would be ideal. But if we make that strong of a statement, we're really not learning from the data that we have received in the past. And so we do want to do some updates and some optimization based upon past data. And so maybe something like this is a more reasonable thing to want. It's saying that it won't have like very much of an effect. And so I'm now going to like introduce a friend who's going to be around today through at least 2 of our talks in the afternoon. And this is differential privacy. And it's a tool that can do precisely this. And it was defined back in 2006 by Dwork, McSherry, Seaman Smith. And the goal is really to bound the effect of just like one sample in some very large optimization process. And so imagine if I have some database D, and it has like a bunch of folks' data, and I plug that into my favorite algorithm, although it has to be like a randomized algorithm. And so this algorithm is then going to like spit out some possible distribution over things that it might produce at the end of the day. And so think of this on the x-axis as kind of like all possible things that may be produced by this algorithm. And this is the like probability that like this algorithm on this database is going to like produce this thing. And so this is really just like a PDF of its outputs. And a property that I would like is that if I were to change one person's data, say I change Chris to be Javier, and I plug in this new database that is the same except for one person's data into my same algorithm, I'm going to have a curve spit out that is close to the original curve. And by close, I actually mean that for all points here, this ratio is going to be bounded. And so this is going to say, I'm going to produce this thing with approximately the same probability if I saw Chris's data versus Javier's. And this should hold for all Chris and for all Javier and for all like friends. And so really this is bounding just the maximum amount the one person's data can affect the output of some analysis. And more formally, it says this. If I have an algorithm M that maps from like an n tuple of types, and so think of this as being like data coming from n people, into some output range R, then I'll say that M is parameterized epsilon differentially private, if it is the case that for all neighboring databases, which are the same except for one person's data, and for all possible things that I might produce, I'm going to produce that thing with approximately the same probability under these two different neighboring databases. And this epsilon appears as a bound on the ratio, and in fact, it's like e to the epsilon. And so this parameter tells me how much can one person's data affect this output. And again, it shows a thing like this, how if I change one person's data, then I'm going to have approximately the same curve, and that approximation factor is going to be managed by the parameter epsilon. And so one really nice thing about this is I no longer have to think about sharing data versus not, but in fact I can like parameterize precisely in between those how much information is being leaked through this analysis. I know that both Simpson and John are going to say more about this later. So this is all that I'm going to say about how this thing works. We'll definitely hear a lot more about sort of like why it works and how to achieve it and why it's a good thing in the next few talks. Okay, and so back to our goal of how to learn auctions. Our goal is really to just privately learn the optimal auction to run. And so there's a series of like various implications that happen. Imagine if I could first privately learn the optimal auction, and by privately, I mean in some like differentially private manner. And that tells me that the current bids have a very, very small effect on the future auctions, because they can say, no matter how you bid or how you might change your data, I'm still going to learn approximately the same thing. And so therefore, people don't really have an incentive to lie, because they can't actually gain much by lying. Unfortunately, they might have an incentive to lie in the current round and just thinking about the game today. And so as long as I design like a truthful one-shot auction, then in fact that will ensure that there's an incentive for folks to be truthful today. And so it's like saying, if you're truthful today, then you will gain. And if you lie today, then you will not gain today. And you also can't really gain tomorrow either. And so there's actually just like no incentive to lie. And so this gives us approximate truthfulness. And so if the bidders have no incentive to lie, then we can go back to our assumptions if the bids are really sampled from the true prior, and we can then apply all these previous results on things like how to learn the optimal auctions based upon samples. And so the real challenge is how to do this thing. And then kind of everything else follows. And so we propose this thing that we call the like online DP auction. And it's very simple. And so for each round, we're going to ask everyone for bids, and we're just going to run the Meyerson auction on the bids from that day. And then we're going to privately update our like belief with these new bids. That's supposed to be subscript. It seems so simple, right? And any questions? It was too easy. Okay, so really at the crux of this is the fact that we're going to choose the auction to run in each day based upon past bids. And so if I can privately maintain that, then we're good. And so we have like reduced this whole complicated question to just like how to privately maintain an empirical distribution. Thankfully, we have tools for that. So there's a tool called like a tree aggregation. And I will say on the next 2 slides, I apologize to both the experts and the non-experts, because to the experts, this will seem like it has no detail at all, and to the non-experts, it will seem overly detailed. So probably no one will be happy, but I feel like it's important to include at least some content. All right. So there's a tool called the tree aggregation protocol. They came actually from 2 papers in the same year, and they maintain online. They maintain a private and accurate count of how many ones I have seen so far in a stream of bits. Very simple. Every day I get a 0 or a 1, and I want to each day tell you how many ones have I seen so far. And it uses a tree-based data structure that allows for less noise to be added. For those of you who are used to thinking about differential privacy, we think about composition, and we're concerned about our privacy budget accumulating too quickly. And so this allows things to compose more log k epsilon instead of square root k epsilon. So it's very nice because our privacy budget grows slower. And you can, in fact, run what's called a two-fold tree aggregation, where you run a bunch of these trees in parallel. And so really, we're going to run a copy of this tree aggregation for every possible value in this histogram. And so I'm going to maintain a histogram of the bids that I've seen so far, and how many times have I seen a bid of this particular value. And my tree aggregation, I'm going to include a 1 if I saw that value, and a 0 otherwise. And so I'm basically going to maintain a histogram where for each bucket, I'm going to privately run this a tree-based aggregation scheme. And so this allows us to maintain privately a CDF of the distribution. And so we now have the tool that we hope for on the last slide. There's a couple technical tricks that I feel are important to at least state for those of you in the room who are curious how to actually apply this. So we apply this to the revenue curve, not to the bids. It's because we actually care about closely approximating the revenue curve and not the actual bid distribution. And we do some rounding, because if I price slightly above your value versus I'm slightly below, these have dramatically different effects. And so I have to account for the noise that is being added due to privacy. And so we round down to ensure good revenue from that. And we also have to prove a key technical lemma, which is that if 2 distributions are close and I maximize revenue for one, then I'm going to approximately maximize revenue for the other. And this is saying that this private distribution that I learned is going to be close to my true one. And so if I optimize for that one, then I'm still going to be doing well in terms of the thing that I actually care about. OK, and so now it's OK to tune back in if the last couple of slides were too much. And so the main result is that we have n bidders, and they each have some values drawn from their own prior, bounded by h. And I have capital T rounds, and I'm ensuring that for each player, they participate in at most k rounds. And we show 3 things. First, this actually is differentially private. Number 2 means that players are incentivized to bid their true values. And so this number is kind of the max amount that they can lose lose by like being truthful. And so think of T as being large, epsilon as being small, and this K and this H as being not too big. And so then this whole thing is close to 0. And we also showed that we're doing well in terms of like approximating revenue. And so this is all really to say, I feel like the main point is that it's actually in the seller's best interest for them to privately run these auctions. And the seller can make higher revenue here than they could if they ignored privacy concerns and allowed players to just sort of like wildly misbehave because they're concerned about their privacy. And so I actually feel like this point is like very important because it says really to all of these like high-tech companies that we're like concerned about them having our data, they will fare better if they give us privacy. And so that's like the main punchline of this. I also like thinking about privacy in some other versions of games, including like pricing and like market segmentation. And the key idea across all of these is to find out how information flows across rounds and make sure that happens in some differentially private way.
So Rachel, first of all, thank you for an excellent talk. I always am impressed every time I hear you.
Thank you.
So in this situation where we're, so I understand the company's perspective, but what about us as researchers? Does this apply? Is there any way for us to translate this into our aggregation of data?
I definitely think so. And especially as we talk about like how to collect data from people, how to gain informed consent. And in fact, this is why I gave like a whole bunch of other examples of games that isn't just auctions, but it's any case in which people have the ability to change the data that they generate for you. And they might want to do that if they're concerned about privacy. And so like one way to make them not concerned about their privacy is to give them strong privacy protections. And of course, it's always a trade-off, because if you give them stronger privacy protections, then you are, in some sense, preventing yourself from doing the kind of analysis that you might want to do. But on the other hand, you're getting better data. And so one property of parental privacy that is extremely nice is the fact that it's like parameterized, and so we no longer have to think about like just privacy or like just accuracy, but it kind of allows you to find that like sweet spot in the middle, how you're giving people good privacy and you're also allowing analysts to have good accuracy as they work with the data. And I think more broadly, this field has worked well because of results like this, how we say, actually, it isn't really like you have to just like throw away data, but it still enables very strong and very powerful analysis tools, and while still maintaining strict privacy. And so it kind of gives you like the best of both worlds. Yeah.
Anyone else? Yes.
Thanks. And maybe you already have plans for this. I'm coming in a little layperson's viewpoint. So how are you planning to sort of disseminate this kind of information to companies where it starts to matter? Is there a plan for that, or is that just we all just have to start working on it?
That's kind of the million-dollar question. Yeah, true, very true. Trillion now. So I'll give you my answer, but I feel like the broader community's answer is kind of the more interesting one. So my personal answer is that I am talking to different companies, and I've been very surprised and impressed at like how many companies actually care about this, in part because most large tech firms who gain revenue through advertising are concerned about things like this. And so this is a nice way to kind of convince companies that it's actually better for them if they give users stronger privacy. But I think like much more broadly, how can we as a community advertise to them and share? And I think it really comes from like events like this, and talking both with academia and with industry and with policy folks, and we'll hear from them soon. Because really, privacy is not a problem that's going to be solved alone by one field, and it really requires collaborating with, having conversations with, and really understanding the like values, tools, and challenges of some other neighboring fields. Yeah.
Okay, thank you very much, Rachel.
Yeah.